Hello, this is Saleh, and today in this talk I'm going to present our work BSRNG, a high throughput parallel BitSliced approach for random number generators. I'm with the Institute for Research in Fundamental Sciences, IPM, and this is the outline of the talk that we're going to cover today. Alright, so as you might know, RNG stands for random number generators, but what is a true random number? So the true random number is basically based on a physical phenomenon such as atmospheric noise or thermal noise or quantum phenomena. For instance, the radioactive decay of an atom could be regarded as an essential pure randomness in the world. However, these methodologies are not so practical and affordable for general purposes when it comes to thousands of computers and users, right? So we have to come up with some other ideas. That's where these pseudo-random number generators, or PRNGs, are getting into games. So PRNG generates numbers that look random, but are actually deterministic and can be reproduced if the state of the PRNG is known. So PRNGs are a computational algorithm that can reproduce long sequence of random numbers. And they are determined by a shorter initial value known as the seed or the key of the PRNG. The PRNGs typically does not rely on sources of naturally occurring entropy, although it might be periodically seeded by natural sources, so you could have some kind of combined true random number with the PRNG, right? There's another kind of PRNG which is called cryptographically secured pseudo-random numbers, which is simply a PRNG with the properties of the cryptography, different kind of properties. And it is really interesting that the CSPRNG or any kind of PRNGs could never be regarded as a true random number generator. But in many applications, including the demanding security critical applications, it is often sufficient to use CSPRNG or PRNGs. And the design of these CSPRNGs are really straightforward. So you have to use any kind of block ciphers or stream ciphers or hard mathematical problems, MP problems, and different ideas as a backbone of a CSPRNG. So there are multiple applications for high-performance PRNGs. For instance, in the cryptography itself, you have a high demand of the high-performance PRNG when it comes to generating the keys, the secret keys, when it comes to masking your data, encryption in the data. Also, in the real-time high-throughput communications, you also need a high-throughput or high-performance PRNG. In chemistry or physics simulations, such as Monte Carlo simulations, there is a need for high-performance random numbers as well. And also in the terabit per second optical communications, random numbers should be available in high performance and high throughput, numbers, high throughput. All right. So the implementation of the PRNG in hardware and software is used for different application. The picture of the left, you can see a crypto accelerator. I think it's the SSL accelerator, where the PRNG module is one of the main modules in the chipset itself. And yet at the further of the right, you could see the random number generator in the Ubuntu OS, I think, which interestingly requires the user to type on a keyboard or move the mouse as the source of the random number to generate the bigger sequence random number string. So what are the algorithms to generate the PRNG software? So in this talk we actually focus on the algorithms based on the LFSR. There are different algorithms. One of the main, which is the LFSR, linear feedback shift registers. LFSR is fundamentally a backbone for many CSPRNGs and PRNGs itself. So it consists of this kind of shift registers that have a certain number of taps as the feedback, and each clock cycle, an output bit is given to the user, and a feedback bit is driven to the shift register itself. So after a while, after thousands of circular shifts, you have a random sequence of bits, and the LFSR is working properly. Also, the LFSR could be represented by polynomial, as could be seen in the equation 1. So CSPRNGs are, as we talked, could be implemented by the use of stream block ciphers, right? This is really interesting and useful because the security primitive of the block ciphers and stream ciphers, including the quality of the randomness of the output sequence, are already studied carefully by the cryptographers. So you don't need to be worried about the quality of the randomness of the output. Excuse me. Also, many implementation of stream block ciphers are used today. For instance, Chacha and FreeBSD or YARA algorithm in iOS and macOS are based on the stream block ciphers, and several standards have been proposed and introduced by FIPS or NIST. So in this work, we have carefully chosen some block and stream cipher as the CSPRNG compatible with the proposed parallel implementation methodology, which will be discussed in the upcoming slides. So first, we have chosen the algorithm called Mickey2. It's a stream cipher algorithm. And as you could see, it is consists of two shift register, 100-bit shift registers. One of them is linear, of course, and other is nonlinear shift registers. And they're controlled by simple function. I mean, not that simple, but simple controller bit R and bit S functions, and they are clocked under each other's control. So this is basically used to encrypt the data, but when it organized in a certain way, it could be also used to generate random sequence bit numbers. The second one is actually famous AES, which is the most famous and used block cipher in the communication today. But for the PRNG purpose, AES is used in the CTR mode, counter mode. And the input data is, let's say, formulated in some kind of a counter, and the batch of 128 bits is generated as a random number in a blocks, while the counter is incremented each time for each AES module. And the third algorithm that we have been developing in this work is the grain algorithm, stream cipher. It's a stream cipher grain algorithm. It's a winner of the stream competition in Profile 2, and it is designed explicitly for the restricted Harvard environment. So it has this kind of really simple hardware architecture. And similar to the Mickey, it is comprised of a single LFSR and a single NFSR, nonlinear LFSR. And we have this function H, which is actually a let's say controller function, which controls the nonlinear feedback registers, and the output bit is generated each clock cycle. So I would like to change the topic for now. When it comes to parallel implementation in GPU, we all know that the GPUs are designed for tremendous number of parallel executions simultaneously. So we have thousands of blocks in a grid, and we have multiple threads in a single block, and all these threads and all these different blocks are executed simultaneously. Okay. Also, we have this kind of a hierarchical memory in the GPU. We have registers within each thread. We have local memory, and we have shared memory shared among all the threads in a single block. We also have global memory, constant memory, and texture memory, which are directly communicated to the CPU. So we have this kind of hierarchical memory in the GPU. By the way, it's the NVIDIA architecture. Yeah, we have this hierarchical memory in the GPU for to ease the let's say execution, parallel execution in the GPU. Okay, but now I would like to introduce a parallelism within the register in the bit granularity, which I call it BitSlicing. So the idea is really simple. The idea is to convert the row major representation of your data, whatever it is, whatever algorithm you're using, to the column major representation. So to make it clear, let's say you have your data stored in D0, D1, D2 up to Dn, and this is the first bit of your D0 data, the second bit, and so on and so forth. So the idea is really simple. You change the representation by storing the first bit of all of your data in D0, the second bit in D1, and so on and so forth. So the same significant bit of all of your data is stored in a single register, right? This is the representation changing, which actually is the basic, let's say, idea of the BitSlicing. So it was first introduced in this data encryption standard by Eli Biham. I think it was around 1998 or something like that. And by this, a simple software trick, the authors were successfully, fasten the performance of the disk for the brute force for 5 folds. It was really, really amazing idea. To give you the picture that how this BitSlicing works and why is it so fast, I would like to study a simple CRC8 example. CRC is as you might know, is a cyclic redundancy code. It checks the integrity of a big input data. So you have a big data and you want to send it over a noisy channel. You compute the CRC of the data, and you send the CRC, and the other end the receiver computes the CRC and verify the integrity of the data in case of any error in the communication channel. Okay, so now this shows a simple CRC8, let's say, architecture. So assuming that we have the 32-bit register, we will need at least one register to store these 8-bit state registers. Also, according to the architecture of this CRC, we will need 3 XOR per each clock cycle, and also a bitwise shift per each clock cycle to shift the registers to get the new input bit. The performance of the CRC is 1 bit input operated on per clock cycle. Now, when this CRC8 is implemented in BitSlice using the fully filled 32-bit registers, okay, we have increased the registers to 8. Okay, so we have used 8 registers. But interestingly, similar to the last one, we have also use 3 XOR per each clock cycle, and we have actually eliminated the shift operation, which is replaced by the reference swapping between the registers in the software. So you don't actually have any instruction for the shift. You just change the reference of the register when it comes to the implementation. Now the output performance of this implementation in a BitSlice is 32-bit input is operated on in a clock cycle, right? So you have eight times more registers, but you actually outperform the conventional CRC implementation by 32 volts. So this is a really simple example of how BitSlice could be used. As another example, let's say you have 32 parallel threads, each consists of a single LFSR. So to generate m pseudo-random bits, you have to overly shift all of these LFSR for m divided to 32 times. And assuming that each of these LFSR has k number of feedback taps, you will need 32 times k bits level XOR operations for all of these LFSR. But when it comes to the implementation of the BitSlice, you will need only one thread to execute, to generate these m pseudo-random numbers as shown in the picture. And actually the number of the bitwise XOR are reduced to k from 32 times to k. The shift operation are completely eliminated, and this is it, a single thread with a reasonable number of registers, and you have reduced your circuit very efficiently. So as you might guess, BitSlicing could be really good in logical operations like AND, OR, XOR, and so forth. They're really good in Galva field, binary Galva field, or extended Galva field numbers. And the shift and rotation operations are really trivial in the BitSlice implementation. But when it comes to arithmetic operations like add or multiply or complex operations, the challenges in the BitSlicing implementations are really there are challenges and there are drawbacks. But the good news is, for each application, for each algorithm, there's always a trade-off which could be used in some of the algorithms and some of the cases. So what we did in this work, we have utilized the BitSlice representation for the multiple block cipher and stream ciphers, like the Mickey stream cipher that we have talked about. So the implementation of the BitSlice for the Mickey and other stream or block ciphers are really hard, because there are there are controls, there are conditions, there are when you try to implement the bits, when you try and implement an algorithm at the bits level, that there's a huge number of registers, and it's really complex. So you can't just go ahead and write down algorithm in a BitSlice level. So what we did is that we have come up with the automation procedure in a high-level transcript, which is written in Python language, to generate the CUDA or C code for the BitSlice Mickey. So after using this automation method, code of 14,000 lines of code was generated for the Mickey BitSlice algorithm. So we have used a similar method for the AES-CTR and the grain stream cipher as the PRNGs, and it's really important to note that the initialization of this algorithm when it comes to IVs, or initialization vector, and keys for each thread should be carefully selected, because these values are critical for the PRNGs and should be carefully computed. Also, for further optimization, we have used shared memory and coalesce accessing in the GPU itself to improve the performance further. So this is the GPU testbed that we have used. We have used 6 different GPUs. The computational power in terms of single precision and double precision, as well as memory bandwidth, are shown in the table. And for the house setup, we have used the conventional Xeon E5 CPU. As the evaluation of our algorithm, we have evaluated and compared the work to NVIDIA's current algorithm, which is NVIDIA's library for generating random numbers. As could be seen in the figure, the Mickey and the Great algorithm outperform the current high throughput random number generator algorithm. But the AES is challenging. Is a challenging algorithm due to its building blocks and complex building blocks compared to the stream ciphers. So in order to compare our work with the other related efforts in the field, we have come up with the normalized performance evaluation, which is basically the idea is normalizing the throughput to the by dividing the achieved throughput to the computational power of the GPU itself, which could be could be seen in the figure as well. Okay. So as for the quality, to ensure the quality of the randomness of the output of our proposed algorithm, we have evaluated our work in a NIST statistical random test, which is a really famous statistical random test. And as you could see, for instance, for the Mickey 2 algorithm, we have passed all of the statistical tests, including the frequency test, the block frequency test, the FFT test, and so on and so forth. All right. So this is really interesting line of research. And as for the future research, we are actually working on other applications rather than cryptography. For instance, let's say error correcting codes when it comes to encoders and decoders in LDPC codes or polar codes, which are in demand of the high throughput performance. Also, we are looking for some kind of automation conversion of the BitSliced, for example, BitSliced compiler, which compiles the code in a BitSliced manner in a compile time, or let's say BitSliced transcript assistant, which assists the coder developer to develop the code in a BitSliced conventions. So with that, I think I will conclude my talk. Thank you for your time and have a good day.